Oh, it's 2 o'clock and there are so many of you already connected. Thanks for being on time, for your interest, and for your time to participate. So maybe we can slowly start. I'm sure there will be a few people who will arrive a little bit late, but let's honor the ones who are on time. So welcome to this first session of the Mag2Pol online introductory courses. For those who don't know who I am, let me just quickly introduce myself. My name is Navid Qureshi, and I'm working in the diffraction group of the Institut Laurent in Grenoble. And today, and for the other courses, I will be assisted by Katie Beauvois and by Edmond Chan. Can maybe just smile and wave into the camera. Katie is part of the magnetism and Newton diffraction group at the CEA Grenoble. And she's also co-responsible of the D23 diffractometer. And Edmond is currently in the last year of his PhD thesis, which was jointly done between the ILL and the University of Edinburgh. And I hope that the words last year and PhD thesis in one sentence didn't put too much pressure on you.
No, it's okay.
Okay, so why did I ask Katie and Edmond to help me? Well, first of all, they are excellent scientists, but they're also very nice colleagues who would never have said no to my question of helping me. That's one thing. And the other thing is that they know Mag2Pol very well, and they have used it on many different data sets. So the idea would be, if you have any questions during the course, that you just type it into the chat, and Katie and Edmond will look at the chat all the time and maybe directly answer your question in the chat or interrupt me, and I will try to answer it myself. Like this, we should be able to clarify as many doubts as possible while keeping more or less on schedule. Talking about schedule, today it will be rather 60 minutes than 45 minutes because I have a lot of stuff to tell you. And you have probably realized the session is being recorded, and I will put the recording on the Mag2Pol website. So maybe, well, the best thing would be just if you could switch off your cameras and microphones so we don't run into any trouble of asking for consents if I put the video online. So that was just a few information. Now I will try to share my screen. I have a few slides before I start with the presentation of the program. And just a few details about what we're going to do today and the next weeks. So this is the outline of the courses. Today we will talk about the general use and powder data analysis. And next week, we'll talk about single crystal data analysis and the different ways of introducing magnetic structures in Mag2Pol. And in 2 weeks, we'll talk about different techniques using polarized neutrons, like measuring of flipping ratios or polarization matrices. And if there are any questions, doubts, or requests which deserve maybe a special attention, then we can have a 4th session at the end of the month for any other business. Today, this is the content. So I'll talk about the basic features of the program, give you an overview, how to input all the necessary things in the main window, the different settings, how to set up a structure model, how do you input the space group, the lattice parameters, the atomic positions. I'll show you how to do quick simulations of reflection lists, intensity maps, and powder patterns. I'll show you how to draw bonds and polyhedra to have a nice looking structure. I'll show you the features of the pattern editor, where you can plot powder diffraction pattern in 1D, 2D, and 3D. And I'll show you how to calculate differences of patterns at different temperatures, for example. And in the end, we will look at some real data and do a Rietveld refinement. So I'll show you the different fit parameters, how to treat the background, how to treat excluded regions, and I have a very quick example of a batch refinement. Here are a few details on what Mag2Pol is and what it does. So to avoid any wrong expectations, I don't want you to wait until the last session and to say, oh, damn it, it doesn't really do what I want to do. So this is what it does and what it is. So it is an analysis software for X-ray and neutron diffraction data, and it treats polarized and unpolarized neutron diffraction data. So it's not a data reduction software. So you cannot integrate your raw data using Mag2Pol. There are some minimum features to merge HKL reflections, for example, but it does no integration. What does it do? Well, basically, you can visualize nuclear and magnetic structures and you can refine them to some data, but that's of course not all. There's much more you can do, and this is why we're sitting here together today and for at least 2 more weeks. What kind of data can you treat? Powder patterns, integrated intensities from single crystal experiments, and polarized neutron scattering, yielding flipping ratios and polarization matrices. So actually, the program was first created and developed for spherical neutron polarimetry data. And that's how the name stuck. So Mag2Pol actually means magnetic structure to polarization matrix. So that was the initial purpose of the program, but it became much more versatile during the years. What is it written in? It's completely written in C++, and based on the Qt5 library. I use eigen for all the vector and matrix calculations. I use QCustomPlot for 2D plotting and OpenGL for 3D plotting. And I use the tiny XML2 library for opening and saving XML files. Where can you get the program? You can download a standalone package for Windows, macOS, and Linux on the Mag2Pol webpage. And if you want any documentation, well, there is the published paper from 2019, but it's of course not as complete as the up-to-date manual, which you can open from within the program. And there are a lot of examples and tutorials on the Mag2Pol webpage. So that's it for now. So that was a very short presentation. I will now open the program and do the rest of the session in a live way. So I will open the program now. And this is how the main window looks on my computer. It may look different on your computer. If it's the first time you open it, it may look like this, because you can actually configure the main window as you need it. You can drag these dock widgets around and place them wherever you think they are useful. You can place them on top of each other and they will create those tab widgets. So you can also close them if you think you don't need them, and you can switch through the different presets in the view menu here. So there are different presets you can use. So I like to use the compact one preset. Like this, I have all the stuff which is related to the input of my data in the upper left corner of the screen. I have most of the screen devoted to the 3D model of the nuclear and the magnetic structure. And I have the lower left section of the screen where I can do simple calculations, like calculating nuclear and magnetic structure factors for a single HKL reflection. Another important part of the main window is the toolbar here, where you have a direct access to most of the features of the program, and you can also change its appearance. So you can again go to the view window and change the icon size, for example. You can determine which of the toolbars you want to see or which of the icons you want to have in the respective toolbars. So the main window is completely configurable, and you can design it as you want and as you find useful. So the most important icon is the last one, the one with the question mark. So if you click that, it will open the manual, which is cross-referenced. You can click on the page, and then you will have a more or less detailed explanation of all the features, and sometimes there are even some links which will bring you to a tutorial video on the Mag2Pol webpage. So that's completely linked and more or less interactive. So let's start. As I said, in this compact view or compact one view, all input related tasks are here concentrated in the upper left part. And I have 3 tabs: symmetry, atoms, and spins. So I'm in the symmetry tab now, and I can enter the space group. So you can enter the space group by its label or by its number, and it's case sensitive. So you cannot write P1, P2, it will not be recognized. And that the program shows that by printing it in red. in the correct syntax, that means with a capital P, it is recognized and it's shown in green. So it minimizes the amount of errors you can do by showing you that the input is correct. You can write 14, for example. That's a monoclinic space group. And if you finish the number with a dash symbol, so I will now press dash, so it will convert the number to the space group label. And you see also for a monoclinic space group, it will directly put alpha and gamma to 90. So it avoids any errors from your side. For an orthorhombic space group, all the angles would be 90. For a tetragonal space group, the A and the B axis will be constrained, which is the same for a hexagonal space group. But here you have the 120 gamma angle. And for example, for a cubic space group, A, B, and C will be constrained to be the same. There are some space groups which have an origin choice. So if you use one of those space groups, you will directly have this combo box to the right of the label where you can choose the choice, the origin. And this is also the case for rhombohedral space groups where you have the choice between rhombohedral axis and hexagonal axis. I meant trigonal space groups. Okay, so let's stay with one of the lower symmetries. I will take a monoclinic space group, put some random lattice parameters. So that's it for the nuclear part, for the crystallographic part. Here, the number of symmetry operators, that's related to the magnetic symmetry operators. And we are not going to talk much about magnetism today. So this will be the topic of next week. So that's it for this part. Now I can go to the Atoms tab. And here I can enter a list of atoms. You can say how many atoms you have. Same as before, you cannot write anything here. It will tell you in red that's not correct. So I can put a cobalt atom at the origin. So these are the fractional coordinates of the atom in the unit cell. You have the isotropic temperature factor here, which you can set to whatever value. And then you have the site occupation factor for that site. And 1 means that this site is completely or 100% occupied by cobalt. Then I will set an oxygen atom at the center of the unit cell and another one on some random position. Okay, I can also put some values here. It doesn't matter at all for the moment. So that's enough already. And now if you want to draw the unit cell, we can click on that icon, or you can go to generate unit cell or use Command U or Control U, depending on the system you're working on. So we'll click here, and that will show me in this part the unit cell. So the controls are relatively intuitive. So you just click and drag to rotate your model. You can use the mouse wheel to zoom in and out. And you can use the command key to move your unit cell around in order to zoom on another point of your structure. And if you click on the right button of the mouse, it will go back to the original zoom. You can also hold down the Option or Alt button and click and drag if you want to change the light position, if this is something you would like to do, and you can Option right click to bring it back to the original position. Then there are a few useful tools here in this 3D plot. You can click on an atom without anything, without any modifier key, and you will see that the atom will be drawn in a slightly different color. That means that it is selected. And you can see in the lower left corner of the main window its position. So that's a very useful way to see which atoms you are actually looking at. Then you can click an atom and shift-click a second one, which will draw a bond between those two atoms, and it will give you the distance in the lower left corner. And you can click, shift-click a second atom, shift-click a third atom, and it will calculate the angle between those three atoms. And you can also click, shift-click, and then drag your model around to search for the correct atom, and then shift-click it. So that's also possible. Then what do we have? So you can decide to show an atom or not, and you can change its color just by clicking on the color here and setting it to something different. Here you realize that the legend is automatically using different numbers if you have different oxygen sites, for example. But if you use the same color, it will automatically just show one oxygen site. And this also applies to sizes. So if I have two different oxygen sites with different sizes, you will have that in the legend as well. Okay, so that's all you have to know for entering a nuclear structure. Now, what do you have to do in order to use a magnetic ion and give some information on its spin? Well, if you know full prof, then you will exactly know what to do. So it's the same syntax. You tell the program by an M that it's magnetic, or J for rare earth elements, and you use the oxidation state. And again, it will become green, saying that it has recognized this element. You can also click here on this icon here, view list, and you will have a complete list of all the elements and isotopes which are included in the program. You can right-click that if you want to sort it in another way. So you can go, for example, on copper 2, and you will have the magnetic and the X-ray form factors. You have the magnetic form factor coefficients for J0, J4, J2, J4, and for those atoms who have J6 coefficients as well. You can click that keep button if you want to compare it to another ion. So you have the magnetic form factors at a glance. And everything you can plot, you can always export. And you can export this either as a PDF file or in ASCII format if you want to plot it afterwards using your favorite plotting program. So as soon as the program has recognized a magnetic ion, it will appear in the spins tab. And today I didn't want to spend too much time on magnetic structures, so I will just enter one coefficient here, which is along the x-axis. I will regenerate the cell, and here we have our ferromagnetic structure. We will see a lot of different ways to introduce magnetic structures next week. So now we have a model of a nuclear.
Sorry, Navid.
Yes.
You have a question in the chat.
Okay, thank you. Well, it doesn't need to know it's something usual. The question was if it needs to know if it's a high spin or low spin version of an ion. It cannot use this information for the moment. So if you say iron 2+, for example, or cobalt 2+, it will take the magnetic form factor and that's it. If you later refine the magnetic moment, for example, and it's low or it's high, then it's for you to interpret if that's a low spin or high spin state of this magnetic ion. But there is no extra information to input in the program. Okay, so we have now a nuclear and a magnetic structure, and that allows us to do already quite a lot of things. You may have realized that many of the icons are not grayed out anymore, so I can actually click them. And I can also do some quick calculations. For example, I can calculate the nuclear and magnetic structure factors of an 020 reflection. So I just type the H, K, and L indices, and I click on Go. And then I see the nuclear structure factor and the total nuclear intensity, which is given as the sum of the squares of the FNs in the case that you have more than one twin. We'll talk about twins maybe next week, if at all. Same thing for the magnetic part. You have the magnetic structure factor, which is a vector actually. You have the magnetic interaction vector, which is the perpendicular component of FM with respect to your scattering vector, which actually contributes to magnetic scattering. And the total magnetic intensity is given by the sum of squares in case you have more than one magnetic domain. So we'll talk about magnetic domains probably in 2 weeks when we will look at polarized neutron data. Then what else can we do? We can generate reflection lists. So if you click this icon here, you can enter your HKL ranges. You can give some constraints on the structure factors you are looking at, or for the different polarization properties you may have. And if you create your HKL list, you have a long list of HKL reflections with different nuclear and magnetic structure factors. So you can also sort that list. So this is quite useful if you are starting an experiment and you would like to know which are the reflections which are very strong, which you can measure very easily. Or you can do the same thing for the magnetic scattering. You can find out which are the reflections which are strong in magnetic scattering. You can do the same thing as a little bit more graphical and visual. You can generate intensity maps. So if you click on that, the program will automatically calculate all the nuclear and magnetic structure factors in a range from -10 to +10 for H, K, and L. And you can plot it in different maps. So here we'll just go from -5 to +5, and that would be the scattering in the HK0 map. I can choose another plane, and I can go through the different planes by clicking on that vertical component. You can zoom in, zoom out with the usual controls. And you see that if you place your mouse over those points, it will give you the coordinates in X, Y. So that's the horizontal and the H and L components in that in this case, and the Z would be the intensity. You can play around with the intensity scale to see weaker scattering here. You can also do a log scale if you want to do that. You can hide the nuclear scattering if you want to see what actually comes from the magnetic contribution. If you want to keep the same scale, well, you remove this, and now you see the magnetic scattering in the same scale as the nuclear scattering. So you see how, in that case, how weak it is. Then there is another feature, which I don't know if it's very useful, but you can change your magnetic structure in the main window. So here I will just change the propagation vector, which will create an antiferromagnetic structure. And if I come back to my intensity map and I click on Add, then you will see how we have some half integer reflections here, which were not there before. So you can add different propagation vector components to the same map if it's something you want to do, or if you have a magnetic structure with multiple Q components. This can also be done using magnetic domains, but we will see that on another day. Then you can do, as I said before, you can zoom in, zoom out. And if you zoom in holding down the command key, then you will project your scattering along this shorter axis. So now you would have a Q scan along that line. You can also do that vertically, and it will create an integration on the L axis. So this is also quite useful to prepare some experiments or compare with actual data. You can save your plot as PDF or ASCII file, and you can also view it in 3 dimensions. Yeah. So the 3D map is actually useful if you have non-orthogonal axis. Just very quick demonstration. So I use a non-orthogonal angle here for the monoclinic angle. I calculate the map again, and if I go to the HL plane, which is still rectangular here in this 2D plot, but in 3D you will have now the real angles between A star and C star. Okay. What else can you do? You can simulate powder patterns. So if you just click on that, it will generate the powder pattern, which consists of the nuclear part and the magnetic part. You have your usual controls. You can zoom in, zoom out. If you hover your mouse over those ticks, it will give you the HKL indices. You can change the source to X-ray to compare what the diffraction pattern would actually look like using the different sources. There's a preset of different instruments, and that's a list which I have to complete. There are a few instruments missing, which I have already implemented in the fitting part, but not in the simulation part. And you can change the configuration of that instrument. you can break down your global pattern into a nuclear and a magnetic part and change the colors if you want to, or the line style, to see what actually comes from the nuclear part and what comes from the magnetic part. So a few useful features for you to understand your powder pattern, probably before you do the experiment, just to know what to expect. Okay. So this was one way to introduce a structure model, and you see it's not very complicated to start from scratch. You don't need to copy any old files to start from for a new compound. It's very easy to introduce the data, but you can also just open a CIF file if typing in is too much work. So you can open a CIF file, which I have prepared here for a compound, which was actually the topic of my PhD thesis. And this will load the space group, the lattice parameters, and the atomic parameters. And you see here, in that case, the isotropic temperature factor is 0, because actually this was a CIF file containing anisotropic temperature parameters. So this is also handled with Mag2Pol. If you right-click on this value, you will see the tick next to anisotropic. So it has a description of the temperature factor, which is a little bit more sophisticated, which takes into account the non-spherical distribution or the non-spherical movement of the atoms. And you can enter the beta values of this tensor, and you can also see the ellipsoid in 3D. And the program will directly analyze the site symmetry of the position where you have that atom, and it will gray out those entries of those tensor which are not allowed by symmetry. So you cannot do anything wrong, because the program will not let you put any numbers here. And if you change that value, for example, well, then by symmetry, that one will change as well. So you can look at those ellipsoids in 3D, and you can also plot them. So I go to the settings here, to the plot tab. You can plot thermal ellipsoids instead of atoms, and that would look like this. Okay. I go back to the atoms. There's one thing I forgot before. If you have atoms on special positions, like the first cobalt atom here, which is lying on the position 0, 0, 0, then you shouldn't do the mistake to move it from that origin, because it's constrained by symmetry. So if you do that and you generate your cell, the program will tell you atomic position 1 is very close to a special position. So that's for you to be aware that you might have done something wrong. And this is just to avoid things like that. So you see here, because of the fact that your cobalt was not exactly at the origin, you will generate atoms which are too close to each other, and that's in principle wrong. So the program will tell you that. And you can also switch that off if you like. So on the symmetry, you can switch off, check special atomic positions, and you can also define which is the shortest allowed atomic distance between two generated atoms. Most of the settings are relatively self-speaking, so it's not too crypted. This part actually just relates what the program should calculate here in these single calculations, and you can change the appearance of the program if you want to have green icons and use it in dark mode, which is sometimes a little bit easier to handle for the eyes. Yeah, so most of the settings are relatively self-speaking. Okay, so back to the structure. This is, as I said, a structure I have been working on a lot during my PhD thesis, and I can tell you that the first cobalt was always light blue, and the second one was always dark blue, so I will change that. And vanadium was always in a grayish tone, so now I more or less recognize what I was working on many years ago. And so now we have a very nice box of colored balls. That means we don't see anything. So it's always good to emphasize the particularities of your structure. So this is a so-called Kagome staircase structure where you have buccal planes running along the z-axis, and you cannot see anything of that. So those buccal planes consist of cobalt oxygen octahedra. So let's draw those octahedra. So we just come here on this icon, bonds, and I click on that. And if I want to draw cobalt oxygen octahedra, well, then I have to look for cobalt oxygen bonds. And I can look for them either element-wise or side-wise. So I will look for all cobalt oxygen bonds in that structure, and it will search for those bonds between 0.1 and 3 angstroms. Actually, I can quickly check what the distance is. It is around 2 angstroms, so that should be okay. So I can just click on apply, and bam, here it is already. I can see those zigzag planes, and I can navigate much easier with the eyes on the structure. So that was very easy to introduce those features. What is this add tick? So if you put your mouse here, it will tell you it adds connected atoms beyond the boundaries. So you see those oxygen atoms were actually added, although it's outside the box, just to complete a polyhedra of an atom which is inside the box. So if I remove this tick atom, it will look like this. So really, we only have bonds which are inside the box, which is defined here above. But so that looks a little bit sadder than before, but it allows me to show you the different styles which you have for the bond. So you can change that to atom 2 color, for example. You can have a bicolor bond or a gradient. You can choose any color you like. Yeah, okay, doesn't look so serious anymore. You can have a larger radius and some transparency if this is what you want to achieve, and you can decide to show the bond or not. So we'll go back to the initial settings, atom 1 color, and I will click again this add button. So here I have my my polyhedra again, and there are different styles for the polyhedra. So no polyhedra at all, face color 1, edge color 2, or both of the same color, which already looks quite nice. I actually will reduce the size of the oxygens, which are stealing the show. So now it looks a little bit nicer. Yeah, so you have different styles. I like the one where I can change the edge color to be something more neutral, something like this. So that looks like a nice plot, which you can export and put into your paper or your thesis or any report. And if you are a perfectionist, then you would like to play with a little some little details. You can move it a little bit more into the corner. And if you would like to have this coordination axis below the label, the legend, then this is possible as well. You come to labels here, and you can move it around. You can also make it bigger. You can make the fonts bigger, also from the legend. And now, just in this particular position, the letter A is on top of the angle of the arrow, so you can even move that around. So that looks a little bit nicer. I forgot there are still some vanadium ions which are alone. So I go back into the bonds window. I add a second bond between vanadium and oxygen. Those are vanadium oxygen tetrahedra, which separate those Kagome staircase planes. And I would like to plot them in that way. Okay, so that looks like a nice figure. And I want to export that. So I just come here on that button, export graphic. And it will be exported into a PNG file. And this is the zoom factor, which actually determines the quality of your figure. It goes up to 25, which is way too much. So 4 is usually of high enough quality. So I will export that with a zoom factor 4. And I will bring, so this is the file which has been generated. It's around 4 megabytes. And if I open it, well, what you see is what you get. It's exactly the same figure. And if I click here, I have the original size. So that's almost poster quality of your structure. And this is only zoom factor 4. You can go way better than that. Okay. Any questions so far? No?
No question, Navid.
Yes. No questions, was it?
Sorry, no question.
Ah, yeah, okay,
Everything is clear.
Okay, everything is clear. That's great. So that was a lot of plotting, a lot of colors and useful things which you can do before your experiment. Now let's have a look at some real data. And first I would like to show you how to look just at the data, powder data in this case. You have the pattern editor. If you click over here on that icon, it will open a new window, which is the pattern editor, where you can load your powder patterns. You can load it in different formats. There's a proper Mag2Pol format where there are some information in the header which you don't have in other formats, so it can be useful to convert it to that. Then there are other formats which are where I have put the ins number. If you know full prof, then it's exactly the same. It will open that kind of files. Now I have data which are stored in XY sigma format, so I choose that. And I will open those 3 diffraction patterns. So as before, you can click on a color to change the color if you want to have a nicer plot. You can decide to show a pattern or not. You can play with the markers and the size and the lines and different things. You can write something in the legend here. So you can click here to add a legend. And here you can say, for example, well, that was taken using a high flux geometry. This was high resolution. And this was high resolution, but 14K, for example. And then you can export your plot into a PDF file. What I wanted to show you here, so these 2 patterns will be the ones which we will refine in a few minutes. And what I wanted to show you is if you look at those 2 patterns, and I can right click here to reset the boundaries, so it will fit the data better into the window. So it's the same compound at 2 different temperatures, and one is above a magnetic transition and the other is below. So this additional blue intensity, or that additional intensity shown in blue, comes from magnetic scattering, and sometimes you would like to subtract the paramagnetic background. So this is easily done here. You can just say 1 times pattern 2 in this case, minus, so I'm here if you wonder, minus 1 times pattern 3. And again, if you do something wrong, it will be written in red, otherwise in green. And then I can create this difference very easily. Okay, yellow is not very nice. Then you can move that around to show it better, or you can remove the other ones. And you can save this pattern just by right-clicking and save pattern. And it will be saved automatically in this Mag2Pol format, which is nothing else than a XY sigma format, but it has a special format for the information in the header. Okay, so as I said, those 2 patterns will, no, not those ones, those 2 will be the ones which we will try to refine now our structure on. So if you want to analyze your data, you come here on this puzzle, fit. So if you open, you click that, you get into the fit window. So the fit window is organized in different tabs. Here we are on the data tab, and the upper part is related to polarization data, which we will see in 2 weeks. The lower left part is for integrated intensities from single crystal diffraction experiments. We will see that next week. And today we will talk about powder patterns. And I will load the first pattern here by choosing the format of the file. And I load for a starter the high flux data. I have it here. The program will ask me, do you want to refine the nuclear structure? Well, I want to refine it. So this is another relic from older times where the program only did the refinement on polarimetry data, where it's not very usual to refine the nuclear structure. So this is still an artifact from older times. So if you click on refine nuclear structure, it will add an atoms tab here on the top. And here you have your structure, which you have input before. So it will directly transfer to the fit window. And you see that there are a few fields which are grayed out. Those are the special positions which you should not refine. So again, the program makes sure that you don't do anything wrong. There are some other parameters which are reserved for single crystal calculations, so they are grayed out as well. Today, we don't have any magnetic data to treat, so there are no magnetic moments here. There are no domains and twins, so we can forget about that. Here you can set a number of constraints if you want, for example, the Z component of atom 2 to be the same, that is to say 1 times the Z component of atom 1. Well, you can do it like this. And you can also use the various keyword, which is at the bottom of the list, and set different parameters, which will be constrained to one parameter like this. So now we will have the Z components of atom 2, 3, and 4 constrained to that one. But we will not need this today. Then we have the patterns tab. So now most of the work will be done here. So we have the upper part, which has some plot controls. Then we have the plot here, where we have, so I can just click on the legend here, the observed data in red, the calculated line in black, the difference between calculated and observed in blue, and we have the peak markers in green, and you can place your mouse anywhere. It will give you the information of the data point below. Then on the right part of the window, we have all the parameters which are necessary. Well, not all of them, most of them, because I only introduced those parameters which I used so far, which colleagues used. So it's not 100% complete. So if you find some features which are missing, just let me know and I will try to implement them as soon as possible. But most of the current or the usually used parameters are already included. And they are grouped in different sections. So you have geometry, background, excluded regions, offsets, scaling, and so on and so on. And it's a good idea to work your way from the top to the bottom. So these data have been measured on D2B, and they have been used or measured using the high flux configuration. So in Mag2Pol, there is a very useful shortcut. You can right-click on geometry here, and you have an instrument list of ILL and ISIS instruments, and I will probably extend that list soon. So I will just choose D2B and click high flux, and it will automatically change my calculated pattern. It will set the wavelength, it will set the profile function, the UVW, and other parameters related to the profile, some asymmetry parameters. So, so that's very useful. But if you have data from another instrument, that doesn't mean that you cannot treat it with Mag2Pol. It just means that you have to type in the wavelength and all these parameters on your own. So this live change or direct change of your calculated pattern actually applies to all the changes you do here. So I see here, for example, the calculated line is way too strong. So I will just change the scale factor to bring it more into a region which corresponds to my data. Maybe like this. And the overall temperature factor is probably not 0, but some non-zero value. Okay. That is getting closer. Now, the next thing I want to do is to exclude those regions which I don't want or cannot explain with my model, like the rise in intensity, which approaches the direct beam, and then the cut due to the beam stop. So in order to include excluded regions, you click here and you activate the excluded regions mode. You will see that with the green border here, so it's activated. So now if you click and drag you can draw excluded regions. And I will draw another one here. You can modify them. If you place your mouse here, it will change into a double arrow. So you can move this around. You can draw them wherever you want, and you can remove them with a right click. And you can also modify the values here. So like this, for example, if you have some precise input, so I will remove that one. And now I leave the excluded regions mode, and now I see those points in gray will not be taken into account in the refinement process. And I'm not really interested to seeing those points, so I will change the plot boundaries. I will just show it from 15 to 147. And now if I zoom in and zoom out, it will go back to these boundaries. Next thing I see is that the background does not correspond at all. So I will go into background mode, which you see over here. So I click and this is activated. I can still zoom when I'm in the background mode. And now I can tell the program where the background is. So I just click to add a background point. And for the moment, I'm in the mode of linear interpolation between points. So every time I click, the pattern will be automatically updated. If I click somewhere where I didn't want to click, I can grab that and place it where I want. And I can even do things like this. And if I don't want the point anymore, I can right click to remove it. So I will just add a few points here. There are different background models. If you right click on the background label here, so by the way, you have seen how this table has been populated with the points which we have just entered. And if I right click on background, I can change the background model. And there is a very convenient thing in Mag2Pol. If you change to one of those models, or especially the next model, which is a polynomial with 6 coefficients. So if I click that, it will automatically fit this polynomial to the line I have just drawn. So you already have your starting coefficients to calculate this line. So that looks good enough. I switch off background mode, I zoom out, and now I can start to refine. So I will refine all the 6 background parameters. So to refine a parameter, you just click, you add a fit flag here. I could click all the 6 or just right click and say check all background. So now all of the 6 are activated. I will refine the zero shift, the scale factor, the overall temperature factor, and the lattice constants. This is enough for the first step. And now to start the refinement, I go to the Fit tab. So here you have a few settings which actually concern cross-refinement or correlated refinement between powder data and single crystal data or polarized data, where you could enter the different weights and then you could drag this point along this weight triangle. We will see that probably next week. So now we only have powder data, so I cannot do anything. It stays here in the corner, and I will just fit. Okay. What do we have? So for each iteration, we will have the reduced chi-square value and the parameter with the biggest step in that iteration. It will tell you if it has converged. It will give you the chi-square, reduced chi-square, and the crystallographic R value, and then a list of all the parameters of your model and of your instrument parameters. And it will conveniently give you the refined parameters with the standard deviation to the significant value. You see here, for example, if the standard deviation is bigger than the value itself, it will just put the whole parameter, the whole standard deviation at the end in parentheses. Otherwise, it will just give you the significant digit. Okay. That looks good. So I will go back to patterns and I will add, for example, the UNVW parameters, well, the parameters which are related to the profile. Click on fit again, so that gets a little bit better. I can refine the position of the sample if it's a little bit off-centered. That gets a little bit better. And I haven't even touched the structural model yet. So I can come here to atoms and click on all the atomic positions. Again, I will use this shortcut to all Y parameters, but I will remove the one from vanadium because it has a very small coherent scattering length for which it is not visible in neutron diffraction, so it wouldn't make any sense to refine its position. I add the Z components of the oxygen, and I fit again, and that looks very good. There's one detail I haven't mentioned, and there's probably one person in the audience who has asked me this question. So that's concerning the asymmetry. So apparently these parameters, which is the sample height over distance and detector height over distance, may cause some trouble with other programs. So it's just to show you that it works like a charm with Mag2Pol. The asymmetry is applied up to a scattering angle of 30 degrees, but you will see here up to 30 degrees, we don't have much information. So it wouldn't make any sense to refine those parameters like this. So I'll say, please apply the correction up to 80. You see how that already affected those peaks. So I will just run that, the fit with the same fit flags again. And now I will refine those SL parameters, but I will remove these flags because there is a strong correlation between those parameters for some data. So I fit that, and you can see in the results here, it has a reasonable value with a very significant standard deviation. And you can also fit the other one. So that works like a charm. Okay, so that looks like a success. Now I've shown you before, I actually have two data sets taken with two different instrument configurations. And it's very easy to add the second data and do a correlated refinement between both patterns. So I just load the second pattern. That would be 14K high resolution. This part will always apply to all the patterns because you actually want to analyze the same structure on different patterns. Otherwise, a correlated refinement wouldn't make any sense. And now on the patterns, you can choose between the first one, which we have already analyzed, and the second one, which we have just loaded. So I will do the same as before. I will change the geometry to D2B, but now it's high resolution. I will bring the scale into some values which look a little bit closer to my data. So now what do I type in for the temperature factor? Well, in fact, I have two data sets at the same temperature, so the temperature factor should actually be constrained, or should be the same between both. So it's very easy to constrain them. I just right-click on scaling, and I can constrain the scale or the temperature factor to phase one of pattern one. So if you have more patterns or more phases, you can choose the corresponding option. So I will constrain it to the first pattern, and you see the value has been set automatically, and it is grayed out, and I cannot fit it anymore because it is constrained to the other value. The same applies to the lattice parameters. It's the same sample at the same temperature, so the lattice parameters have to be the same. So I right-click on cell, and I constrain the lattice to pattern one, and that's it. Same as before, I will add some excluded regions like that. I will concentrate on the part of the pattern which I'm actually interested in. I add some background points. And this time I will just stay with this model of a linear interpolation. I remove the background mode, and okay, so now I start the refinement. I check all the background positions. I refine the 2 theta offset, the scale factor, and that's enough for the first step. And now I can choose which pattern I want to see here in the fit window. So I will change it to the second one and click the fit button. Okay, it's getting better. Now I will add the parameters which concern the peak profile. And that already looks like a success. That was very easy to do. And you can compare the two patterns here. You can compare them. You can compare them here. You could export your patterns as a PDF file or as an ASCII file if you want to replot it afterwards. So that was a short example of how to analyze a powder pattern and also to correlate it with another pattern using the same structure model. Any questions so far?
No questions.
Okay. Then that's it for this example. So the most important thing is don't close your window right now. This is almost what I have done, because your progress is not saved. For the moment, you have to accept it. So here you have this accept button. As soon as you click accept, your refined parameters will be transferred to the main window. And you have some other options here. You can view your results. So here you can see the nuclear structure, well, the intensities calculated and observed to theta values for all the HKL reflections which are inside your pattern for the two different patterns here. You can export your results into ASCII file. You can see correlations between your fit parameters, and by default it will mark those correlations with more than 70%. So you can analyze what you are actually refining and if it doesn't make sense. So it's very, very easy to check. You can change that number and then you will have a different color code. You can export this graph. And if you do a refinement and then you're not happy with it because you have parameters which diverge, or you cannot recover the initial values which you have, you can always undo your fit, and it would bring you back to the step before having clicked the fit button. I am happy with this fit, so I will click accept. So you can see here, for example, pay attention to the atomic positions here. For example, that one is 0.229. If I accept, so I will have transferred the refined values to the main window. I can close that window, and I can save the file, which I should have done already earlier, because it's always good to save the progress.
Yeah, I interrupt you because there were like several questions which just pop up in the chat. So
okay, how to add two phases in a single refinement? I will show you just in a second. Is it possible to simultaneously fit XRD and ND of same sample? Yes, of course. I will show you also how to do that. Is it possible to do BVS-like calculation? Bond valence sum? No, it's not yet included. Can you batch fit multiple files of the same sample? Yes, I will show you that in 3 minutes, maybe. And when you refine two patterns at the same time, how do you define the weight? Okay, very good questions. I go back to the fit window, where still everything is loaded, because you don't lose your progress after clicking accept. So here you have the weight, and if I do a right click, I can delete my data, I can replace it, or I can change the weight. So if I click change weight, I can enter a new value. What else? How do you refine neutron and X-ray data? Well, you just choose X-ray here if it's X-ray data. And did I forget something? Ah, yeah, the batch fit. This is the next example. No, how do you refine several phases? So if you want to add a second phase because you have realized that you have parasitic peaks, or you actually have a phase coexistence or anything of that sort, then you right-click phase here, and you can add a phase, either a new phase or you duplicate the current phase if for you it's easier to change that because it's very similar to the current phase. So I just click new phase, and yeah, I don't know, maybe we want to refine some aluminium, which is somehow in the pattern. So I can choose aluminium as a phase. Yeah, this is one thing I forgot before. Here I have to transfer the cell to the powder model. I will explain in a second why. And now if I go back to the fit window, you will see that now I have the peak markers for the main phase, and I have the peak markers for the aluminium phase, which I have just added. So you can add multiple phases just like this. Concerning this transfer of cell parameters, I can change back to this one. So something's not wrong. Yeah. So if you refine a powder data pattern, a powder pattern, it's not directly transferring your lattice parameters back to the main window, because you may want to use those lattice parameters for a single crystal refinement. So you don't want to mix the data or the results, but you can actually transfer it if you click on transfer cell from powder model. So you can bring back the refined patterns, the lattice parameters to your main window.
And Navid, is it possible to do le by fit?
Not yet. I was thinking to implement that very soon. Okay, so there was another question about batch fitting, and that was something I actually had on the program. So I will show you first the data. This was on iron arsenide superconductor, also many years ago already. So here we have the data. It's a temperature dependence, and we have measured different patterns between 5K and room temperature. So I will open all of them. And we were interested in a structural phase transition from a tetragonal phase to an orthorhombic phase, which can be very nicely tracked by looking at the splitting of a certain peak. This certain peak is at 68 degrees into theta. So here you have all the patterns in different colors, and you don't really see much. So there are a few features that you can use here. So I can change the boundaries. I can offset, for example, this one like this. And I can right-click on this delta Y and set a gradient. And now I can see a little bit more clearly what is happening as a function of temperature. I can do the same with the color. So I can choose, for example, blue for the coldest color temperature and red for the warmest. And I right-click on color and set a gradient. And that looks a little bit nicer. I can remove the markers, apply that to all the patterns, and use thicker lines. So that looks quite nice. I can add a label, a legend, and right-click here on legend and set the temperature, which you can also modify if you don't want to have decimal points, for example. So that's all left to you. And this is already a quite nice plot, which you can put in a report or in a logbook. You can also look at it in 2 dimensions. So you see the splitting here on this in this color map, and you can also see it in 3 dimensions if that brings you anything more, but at least it's possible. So we will have a look at this peak splitting, or actually we will refine the diffraction patterns at the different temperatures. So I have already done this for a single temperature. So this is the structure of this lanthanum iron arsenide superconductor. And I have refined the 5K data using a linear interpolation of background points, a scale factor, and lattice constants. And I have refined the Z components of those positions which are free by symmetry, and an isotropic temperature factor for each of the atoms. So the fit looks good. I accept, I close. So this is nothing new because I have already done it before. But now, if you have a powder fit already loaded, or you have just done one, then you can enter this batch fit window. So I click that, Now I have a miniature version of the fit window here, where I can actually only do plotting things. And here I can load my different powder patterns. So I will load them all at once. And I can go through them. If you see on the right side, the patterns will change. The calculated line does not change because I have only one fit at 5K. Actually, I will directly concentrate on that peak splitting I've shown you before. So you see how that changes as a function of temperature. So the data are already sorted by name, but you could sort them if you have that information in the header and the metadata, then you can sort it by temperature, by sample temperature, regulation temperature, or set point. If you use the Mag2Pol format and you have entered a doping dependence, then you could also sort it by doping dependence. So I will sort it according to an ascending sample temperature. You see now, you see the temperature which has been loaded or read from the metadata. And now I can do the fit batch using this option where the refined value of one fit will be the starting values of the next one. And if your jumps in temperature in that case are not too big, well, then actually that should work quite well. So I click fit batch and it will now fit all the patterns, and you can see how it changes here already in that window. You can go back and see the fitted line and the observed pattern. You can see here how your refined parameters change, and they're already given with the standard deviation. And you can directly plot this temperature dependence. So I can click on the A lattice parameter and I click on B, and I can see very nicely how they split from a tetragonal symmetry to an orthorhombic one. I can add the C lattice parameter. Well, now I don't see anything anymore, so I will plot it to the right y-axis. And as before, the controls are very similar. I can change the colors very quickly to make it look a little bit more to my liking. And you can change the labels like this, for example, and that's it. You can export this plot either as PDF or ASCII. So this is a super quick way of doing batch refinement and to look at your results just with a few clicks. So yeah, that actually concludes the first session. I hope there was not too much information, or at least that you are motivated to try to do something on your own using Mag2Pol.